Welcome everyone to the first NERC Centre for Doctoral Training in Oil and Gas online seminar. Like many others out there, we are attempting to embrace this new online world while also providing a resource that can showcase the research being carried out by the CDT community. So for the first seminar, we have the widely professed Queen of Zoom, climber of scree and fieldwork aficionado, Zoe Cumberpatch from Manchester University. Zoe is a member of the 2017 CDT cohort and pioneer of the online seminar. She is researching deep marine sediment routing around actively growing salt structures, and as such, confinement is not a new concept for Zoe. Famed for her fieldwork photography, her talk today will help to remind those whose research and training has included fieldwork that our beautiful field areas are still out there and will remain so until we're safe to go outdoors again. So please allow me to officially introduce the first CDT virtual seminar talk, Evolution of a Mixed Siliciclastic-Carbonate System on an Unstable Margin, the Cretaceous and Eastern Greater Caucasus of Azerbaijan. So over to you, Zoe.
Okay, thank you, Anna, for like the best introduction I think I've ever received. So as Anna said, my PhD is actually on deep water sediments and how they interact with salt tectonics. But what I'm going to talk to you about is something a little bit different. So myself and Ewan Suter, who is a 2016 intake of the CDT, we won a CASP grant to go and do some exploratory fieldwork in Azerbaijan in August last year. So we were there for a month, and that's what I'm going to present to you today with our findings. It's actually been, we've submitted this to Basin Research and got the reviews back over the weekend, so hopefully it will be available for you to look at if you are interested in the near future, and it's on Earth Archive already. So just to bring everyone to speed of what we mean when we say a sediment gravity flow, we've got a video here from the flume tank in Utrecht. If you think of it as a swimming pool full of sand that's injected into, so like producing a landslide from the upper part. I'm just going to show it now so that this is what we're talking about when we say a gravity flow deposit. When sediment-laden water is moved from the continental shelf to the basin floor over time, initially as a channelized geometry before radially spreading into more of a fan or lobate geometry. Initially quite erosive in the channel, depositing high density turbidites in the lobes, and then coming out as we're sort of diluting now, we're depositing more distal, lower density turbidites. So this is what we're talking about when we say a gravity flow. And these tend to, I don't want to watch the video again, come on. These tend to deposit themselves as fans or deep marine lobes, which you may have seen figures like this before. They're quite useful in predicting where we're going to see highest quality reservoir sandstones, so in these kind of areas here, and also for predicting types of diagenesis, amounts of clay coating, all of the type of things that I'm sure Claire's going to talk about a little bit later on. But these are generally quite a predictive model, and it's well understood for unconfined, so flat basin floor, siliciclastic, so sands rather than carbonate sands, basins. So our research group, Ian Kane's research group at Manchester, that myself, Ewan and Ash from the newest intake of the CDT are all in. We work on how these deep marine sediment gravity flows interact with topography. So where the basin isn't flat, where there's a hill caused by salt topography or caused by fold and thrust belt topography. And we do this in a variety of different ways. So we've looked at them in physical models like the flume tank, numerical models, subsurface studies, and also field-based studies. So in height of the fact that we really like topography, and that's what we work on, we were interested in the Azerbaijan study area because it gave the opportunity to look at a confined or a topographically confined mixed system. So these are typically less well documented than their siliciclastic counterparts. So there's a lot of work done in the Karoo, in South Africa, a variety of different subsurface settings for deep marine siliciclastic systems, but not a huge amount of work done for when they interact with a carbonate system. And we actually think that they may be common globally and misinterpreted as this kind of siliciclastic to carbonate transition zone, when in fact there's a long-lived mixed system. So the key questions we were trying to address in our month in Azerbaijan was, how do these mixed systems interact with confining topography? Is that similar or different to how our individual siliciclastic systems interact? On what kind of scales do we see mixing? So do we see it on grain scale, bed scale, seismic scale? And how do our mixed globes differ from their siliciclastic counterparts where all of the work has been done? And that's in terms of those broad geometries that I just showed, so where the axis is and where the off axis is, and also how they stack. So before I take you to Azerbaijan, we're going to go to an offshore analogue from the Gambia. So this is some of Max Cassen's work from Manchester from the North Africa Research Group. We're in a passive margin setting here that's been that way since the Jurassic. But if you look on this, this is a top structure map, we can see that we've got a carbonate platform with siliciclastic canyons feeding into a deeper basin. We can, on the seismic line, see a talus deposit, so as well as some onlaps. So these are key features that we expect in these confined settings. And if we look at some RMS maps, so reds and yellows are things that are quite different, blacks are things that are quite similar. We can start to pick out that within these carbonate systems here, we've got these blocks that are thrown into the system. So we've got some kind of failure going on in these blocks being deposited that are interacting with another contemporaneous siliciclastic system. And we went to Azerbaijan to find basically examples of this in the field. So where those blocks look tiny on the RMS maps, they actually form the entirety of outcrops in the area we were working in Azerbaijan. So you could see that if you were looking at something that potentially represents one failure block in seismic, it might actually represent an entire boulder bed field in outcrop or on a sub-seismic scale. So where were we in Azerbaijan? We were in the Eastern Greater Caucasus Mountains between the Black Sea and the Caspian Sea that run through Azerbaijan, Armenia, and Georgia. Much of the basin fill is Mesozoic, primarily Jurassic and Cretaceous, related to a series of compressional and extensional events. And this has all been brought to the surface by the Caucasus Mountain Belt mountain forming event in the Oligocene, which allows the area to be divided into a series of fold and thrust regimes and kind of structural areas, of which we focused on one of them. So we specifically focused in this area, so the easternmost Greater Caucasus in Azerbaijan, quite near the Russian border. And the stratigraphy we were focusing on was mainly the mid to upper Jurassic limestones and the Cretaceous basin fill, and specifically in the Konarken zone, structural zone. So this is a section from quite close to our field area. We've got deformed Jurassic limestones, but we've also got the specific section we were focusing on where we see a upper Cretaceous Paleo Valley cutting into the lower Cretaceous and the Jurassic erosion rate. And the first fill of the Buduk Trough in its own strict sense, which is the area we studied, the Buduk Trough, was the Cenomanian-Turonian. And this is commonly a conglomeratic contact, but across the study area, it's very variable. So it's actually conformable above Aptian deposits in this vicinity, and in Kurt, which is just here, it's erosional into the Barremian, and it's completely absent at Shek. So this kind of depositional variability was what was given as the evidence initially that there was some topography there, and we wanted to understand what caused that topography. Like all sedimentology studies, we identified facies first. So we identified 10 different lithofacies. Some of these were purely siliciclastic, so a low density siliciclastic turbidite. Some of them were calcareous, so medium density calcareous turbidite, and some of them were more mixed. So for example, here, there's a slowly eroding calcareous turbidite with a punctuated high density siliciclastic turbidite running through it, and we see the similar thing here. And as we would expect in deep marine environments, we see all range of flow dynamics causing all range of flow deposits, such as turbidites and debrites, failures, etc. So using our fascies, we managed to identify 7 fascies associations. Some of these were initially siliciclastic, so they were in the Cenomanian Turonian. It was mostly a siliciclastic system. And then in the Carnation to Maastrichtian, we start to see the evolution of a more mixed system, so an introduction of more carbonate grains and a potential carbonate source area. So just looking at that Cenomanian to Turonian, so the purely siliciclastic successions, we have typical lobe fringe deposits, so very, very thin bedded. We've got huge channel axis deposits here, so with kind of conglomerate clasts in the channel fill, as well as large scale mud clasts. And then in the channel margins, we see quite similar to lobe fringe, but a much coarser fragment, telling us that we are closer to the kind of external leve of the lobe fringe of the channel margin. In our Carnation to Maastrichtian succession, so we're starting to see more of a mixed environment. We're also starting to see the development of more lobate deposits rather than a channelized system. And we see in here the change from siliciclastic mud to more of a calcareous background mud, and the interfingering of siliciclastic thin beds and medium beds, depending on which part of the lobe we're in. So in here, for example, we've got some limestone class and some sandstone class within these conglomerates, and within this succession here, some of those thin beds are calcareous and some of those thin beds are siliciclastic. So one day we decided we were going to count lots of clasts within the conglomerates. So within our conglomeratic succession, we can see that as we go up stratigraphy from the Cenomanian to the Maastrichtian, we're initially in kind of our 50-50 siliciclastic carbonate situation, but we seem to evolve into our cluster becoming more carbonate rich as we go through time, given the further indication that not only are those fascies associations changing to become more mixed, but the entirety of the system is changing and seeing an increase in carbonate material. So anybody who has worked on deep water systems will know that lobes can stack in a variety of different ways. And these help us infer what's kind of happening with our sea level. So there's 2 examples here of either lobes can either thin upwards, showing kind of retrogressive change, or they can thicken upwards, giving a more of an indication of a progradation and the build out of a system. And we wanted to see if we could decipher that in the mixed system. So you can see this in siliciclastic systems such as Anot and Bacchio, where I work, but we wanted to see if that's actually the case in in mixed systems. So this is a nice complicated graph chart here, but essentially it represents there's 3 different settings. So the northern margin, the axis down the middle, and the southern margin. Blues are carbonate, oranges are siliciclastic. The top shows bed thicknesses, the bottom shows grain size, and the key thing to take is there's basically no correlation. So if these things were kind of thickening or coarsening upwards, we'd expect to be seeing a statistical significance in the R squared, but we're seeing things very, very close to 0, suggesting that they've kind of been modulated, or that there's very difficult to decipher any trends, which we'll get back to later on. So I started this presentation saying we would love topography in our research group, so it'd be wrong to not mention a few pieces of evidence for the topography. So we have in the field, we can see onlap, similar scales to the type of things you might be expecting in subsurface. We can reconstruct that as a 6-degree slope. We can see evidence for ripples reversing. So this is where the deep marine system is flowing in one direction and then rebounding off of the topography. We can see differential run up of different parts of the flow. So here we've got the debris flow isn't able to run up as much as the lower density turbidite on the slope, and that's quite common in topographically confined areas. We can also see stratal terminations, both downlap and onlap, of conglomeratic bodies in these systems, again, very typical of these kind of failures, these failure environments. And we can also see mass failures, so these are slumps folding to the south, which fits with our regional interpretation of a northerly paleo margin. So those models and these figures here and the amount of topography give us the indication that we've got hundreds of meters of topography on the basin floor while these flows were being deposited. And how could these have been formed? So there's potential for this topography to be formed by a fold over a thrust, from a normal fault failure, or alternatively from some kind of allochthonous block, so a big mass transport deposit that's already deposited in the basin, forming some kind of topography. And there's basically very little evidence for any compressional or extensional event during the Cretaceous in the area, which leads us to think that the allochthonous block is the most likely option. If we think of that in kind of a 3D geometry rather than just that there. So there's blocks around the study area. So here we've got all these kind of blocks of various sizes, so they can kind of hidden in the outcrop here. And anyone who follows us on Twitter will know that it's not a megaclast unless you and Suta is sat on it. So a variety of scales of the blocks seen in the area give us the evidence that this might be the most likely theory. Also in Azerbaijan, so just out of our section here where this line is the largest mountain in Azerbaijan that's vastly turning into a ski resort, Mount Shadag. And that the interpretation of Shadag is that it's a kilometer scale elystrostome block. So again, this gives us evidence that what we're looking at may be also very similar. And if we look at an outcrop, photos from different orientations, you do kind of see the evidence that this is quite a rugose contact, and potentially it is something that is a mass failure. So that's nice evidence there. So trying to bring that together in how the story evolved and through geological evolution through time, we initially had a very muddy slope that appears to have shed some kind of mass transport deposit into the basin. During the Aptian to Albian, we have a siliciclastic system depositing thin beds that appear to sort of onlap this topography. In the Cenomanian, we believe there's a slight increase in sedimentation, so we see a coarser grain size fragment, possibly related to some kind of compressional event leading to uplift. So we start to see the development of these submarine channels and their associated levees that cut into the mass transport deposit topography. And then as we move up into the Canadian to Maastrichtian, we start to see the system is becoming a lot more mixed. We start seeing the build out of these carbonate systems and the interaction of the two systems. And that's why we see such variability in the different locations, because eventually by the Canadian to Maastrichtian, we're actually healing the topography adjacent to the mass transport deposit, whereas further out, we're actually seeing more of the effects of the siliciclastic channels, but longer lived. So what does that actually mean for these lobes? So there's that figure again, but I'm now just going to try and make a point about when they're mixed, what might happen. So if we bring back up the RMS maps, we can now, from what we found in the field, kind of overlay these two different interpretations. So the siliciclastic lobe here is brown, the carbonaceous calcareous lobe is blue. And it basically, what we would typically say in a siliciclastic system is that we're in the lobe axis or the lobe off axis, and that will have an interpretation for reservoir quality. But when we have a mixed system, so for example here, we would be seeing the highest quality reservoir sands of the lobe axis for the siliciclastic system, but they're going to be interbedded and modulated by these muddier calcareous muds. So what that might look like in a log, and therefore what we might sort of expect to see in core, would be a lot more complicated than what you would be able to predict if you just have an individual siliciclastic system or an individual calcareous system building out. So it makes it very, very difficult to study, make a predictive trend on whether one system is prograding, one system is retrograding, and therefore where you're likely to find your better quality reservoir depositional elements. So to conclude, the Buduk Trough in Azerbaijan evolved from a siliciclastic dominated to a mixed dominated deep water system throughout the Cretaceous. There was a persistent lower Cretaceous high forming the topography, which we believe was formed by a mass transport deposit. And that's expected to have influenced sediment routing during deposition, as we have hopefully just shown. There's a huge subseismic variability evident from field-based studies of the type of carbonate blocks you can see. So here we can see they're just a couple of loops in seismic, but in the field they dominate outcrops and are commonly associated with more failure up or down dip. So they can maybe be used as predictive, which is something we touch on in the paper, but we've not covered here. System mixing is multiscalar, so we see it on a Fasces scale, we see it on a Fasces association scale, you can see it here on a seismic scale. So there's mixing on all the levels, which needs to be considered when we're looking for reservoir quality. And then it's particularly difficult to predict mixed systems predicting their load stacking patterns because they seem to modulate each other, and also because of their modulation with each other and the interaction of topography, it's very difficult to predict where you're going to see a better quality sandstone laterally, for example. So thank you very much to Casp, who funded this part of the work. Chuck's a goal, which is Azuri, for thank you. And does anybody have any questions?
Sounds like there aren't any questions, Zoe, but just wanted to say thank you very much for putting together such a fantastic 15-minute resume of this piece of work. And it's really good to see Casper funding things like this in the field and what you can get out of it in a relatively short time. How did you happen upon this area as being a good one to go to as an analogue for some of these carbonate blocks?
So Nigel Mountney from Leeds had been there in, I think, 2010, and Ian had seen the photos from this area. So I think Nigel had gone on a field trip after a conference. And Ian had happened to see the photos of this, and he was trying to, while Ian was working at Sattel, he was trying to propose it as a field area for them to go to look at topographically confined basins. But due to kind of some political issues over there, that never quite got bought by them. So when we saw that CASP were announcing these grants, Ian suggested that it would be a really good area to kind of compare between the three systems. So because Ewan works on fold and thrust belts and I work on salt topography, and this was another example of topography, it was going to be a good opportunity for us to compare the different types of topography, and such as kind of, do the deep marine flows care what the topography is, or are they just reacting with some topography? And it wasn't actually until we got out there that we realized it was a mixed system, because there's very, very, very little literature, and even less of that is written in English. It's all very old Russian stuff. So it was quite a nice exploratory frontier field work kind of thing, which was great fun.
Yeah, tremendous. No, well done.
Thank you.